All right, now we're going to use some of the information we learned in the last chapter and look at image formation. Basically, we'll be concentrating on mirrors and then lenses. This first video is focusing on mirrors. So I had to include this because this is a picture from your book, but it's a good example of a surface that's curved, that reflects and produces images. We all know it's called the bean. Who knows it as Cloudgate? Alright, so first of all, let's think about plane mirrors. A plane mirror is just a flat mirror. And we learned in chapter 1 that when light hits a mirror, the angle of incidence is equal to the angle of reflection. That's the law of reflection. So let's use this and start thinking about how an image is formed. So we started off pretty simple with just a point P, and imagine that light rays are coming off at point P at many different directions. Now, if we allow each one of those light rays to reflect using the law of reflection, we can then see a whole lot of reflected light rays. Now remember what I told you, is when your eye sees these light rays, in your mind it traces it back to where they would originate. And so if we trace all these light rays that are reflected backwards behind the mirror, they appear to come from this point right here, and we're calling that point P prime. Now P prime is where the light rays that are reflected appear to have originated from. And so this is where an image of P would appear to be located. And so notice, and this is something that we'll be talking about with mirrors and lenses, notice that the image appears to be behind the mirror, but we know that light doesn't pass through the mirror. For this reason, we would call this image, we would call it a virtual image. And we're going to talk and come back to that idea many times in this chapter, what we mean by a virtual image. In a sense, it's an image that appears to be at a location where it actually couldn't be because light isn't actually there or wouldn't have come from there. So now we use that idea of reflection or the law of reflection to see how a single point could produce its image. Now let's look at something a little bit more realistic. Not really sure why they choose a pill bottle, but that's the picture from your book. So okay, now here we have an object. And another thing now that we want to kind of call your attention to is this right here. This stands for the object distance, and that is the distance from the object to the mirror. Seems obvious. And so they just chose basically sort of like the mirror problem that you asked me today. You choose the bottom of the pill bottle and the top and just draw two light rays coming in, hitting the mirror and reflecting using the law of reflection, then tracing those reflected light rays back, and that's where they appear to have originated from. And for that is where an image of the bottom of the bottle would be formed. Similarly, we have two light rays coming from the top of the bottle, and then we see how they reflect and where they appear to originate from, and that's where an image of the top of the bottle comes from. The idea being that everywhere in between the top and the bottom would be giving off light rays that would reflect and help fill in the image between the top and the bottom. Of course, if we did all the light rays, it would be hopelessly complicated, and so they're just trying to keep it simple. Notice here also, this distance right here represents the image distance. I don't know if it's obvious, but when you look at it, you might notice that in this picture, it really does appear that the object distance and the image distance have the same magnitude. That is, the distance that the pill bottle is located from the mirror is the same as the distance that the image of the pill bottle appears to be from the mirror or behind the mirror. Again, this is a virtual image because while it appears that that image is behind the mirror, no light goes through the mirror, so it couldn't actually be coming from there. It's simply because of the reflected light rays, and your processing in your brain assumes that the light came to you in a straight line. Okay, so one of the things I mentioned in the previous slide was that these two distances are equal. That is, the image distance and the object distance are the same. What I didn't mention, but is related, is that the object height, or the image height, and the object height are also the same. And so in this case, we say there's no magnification. That's another thing that we're going to be looking at when we talk about images, is whether they look bigger or smaller, and also whether they're upright or upside down, because that does happen. So just to come back to this idea of the image distance and the object distance, I was pretty careful to say that they had the same magnitude, but if you see this expression, which is relating the object distance and the image distance, you see the negative sign, and that might be troubling to you, except that what is true is that the image distance that we would give would be negative because of the fact that the image appears to be behind the mirror, and so that makes it a virtual image. One of the ways that they also talk about it is that the image is not on the same side as the outgoing light. The idea that the reflected light, you would expect the reflected light rays to come together to form the image, but they don't. They actually appear to have come from a common point. And again, that's another way of thinking about why it's a virtual image. And again, keeping in mind that the image distance is negative for this plane mirror because of the fact that it's behind the mirror. Now, we don't just have plane mirrors, we also have spherical mirrors. And a true spherical mirror would literally be like just a portion of a spherical surface. Basically we can have them two different ways depending on where we're putting the reflective surface. If the reflective surface is on the inside of the mirror, we have what we call a concave mirror. And if the reflective surface is on the outside of the spherical surface, we call it a convex mirror. Now, one of the things that we will talk about with both lenses and mirrors is called the focal length. And in this picture, we have three different examples. In general, the way we define the focal length for a mirror is if you have parallel light rays coming into the mirror and reflecting off of the mirror, the common point where those reflected light rays would intersect is called the focal point, and then the distance from the mirror to that location is called the focal length. Now, in this picture, they show three possibilities. A parabolic mirror reflects the light very nicely to a common focal point. And again, so here's the focal point, and then the distance from here to the mirror would be the focal length. They point out that in the middle picture, if you have a really large spherical mirror, and large would be like considered by the R, which is the radius of curvature. That's basically, if it was a full sphere, what would its radius be? For a large spherical mirror with a large radius of curvature, the light rays don't intersect perfectly at a single point, so we don't like those. But if the mirror is relatively small, then then our focal length, they all converge to the focal length. Something that I want to tell you, because I didn't see it anywhere else, is that the radius of curvature and the focal length are related by this expression. So when we're talking about spherical mirrors, we're going to be talking about small spherical mirrors where we do have a definite focal point. Oops, sorry. Now the picture that you saw on the previous slide was what we would call a concave mirror, but we also have convex mirrors. A convex mirror doesn't actually allow for the light rays to converge when they reflect. They actually spread out. As you can see, these reflected light rays are sort of spreading apart. And so in order to find the focal point, we have to trace them backwards. Behind the mirror is where they appear to intersect. And so because of the fact that the focal point is behind the mirror, that makes the focal length is negative. So we also can call it a virtual point. Another thing to keep in mind is because of the way a convex mirror reflects the light rays and because they never have the chance to intersect once they reflect, any image that is formed by a convex mirror will be virtual because all the images will be here behind the mirror instead of in front of the mirror. A concave mirror can actually produce an image in front of it. When the light rays reflect, they can intersect, but a convex mirror cannot. And so here I actually have that sort of summarized. So a concave mirror is a converging mirror. It will have a positive focal length. Usually concave mirrors will produce real images, but if you have an object placed very close to the concave mirror, closer than the focal point, it actually will then switch to a virtual image. For the convex mirror, it has a negative focal length because of the fact that it diverges. It causes the light to separate when it reflects, and it will always produce a virtual image. Here are some ray diagrams, and I actually did give you some older videos where I went through the process of drawing ray diagrams for mirrors and lenses. And so there's sort of like 3 or 4 very typical rays that you can draw in a certain way to figure out where, given an object at a particular location, where will the image form. And notice here in the top picture we have a concave mirror, so it's going to form a virtual image. Notice that the image is here in front of the mirror, and so that makes it a real image because the light rays actually converge to form the image. Notice also it's upside down. Usually we say it's inverted. And also it's smaller than the object, so another term that we use is that it's reduced. And the bottom picture is a convex mirror, so we'd never really expect it to form a real image, but if we take our light rays that we've drawn and we trace them back behind the mirror, it appears that they intersect at this location Q prime, and that's where our image will be. This is a virtual image. It's also reduced, but it's not inverted, so we say it's upright. And so here is another picture showing in more detail some of the geometry that you can use to figure out the relationship between the object and the image and how it's formed. We don't generally do ray diagrams as a practice, but sometimes it's handy to be able to sketch them very quickly to get a certain idea of what it might look like. Usually we're going to use the mirror equation for mirrors that we'll show you in a minute. So, for instance, here's the mirror equation where d sub O is the object distance. That's the thing that we put in front of the mirror. D sub I is the image distance. That's what we're forming. And F is the focal length. And so most of the, for mirrors, our object distance, I think, almost always would be positive. I can't think of an example off the top of my head where it wouldn't be. D sub I is positive when the image is in front of the mirror. And then that makes it a real image. D sub I is negative when the image is behind the mirror. And that's a virtual image. The focal length is positive for a converging mirror. That's a concave mirror. And the focal length is negative for a diverging mirror. That's a convex mirror. So a lot of times we can approach a problem. You basically are given two pieces of information, two distances, whether it be a focal length or an image distance or an object distance, and then you find the third. That the value of that will tell you where the image is, and it also tells you if it's real or virtual. Another thing that we like to know about is, as I said, sometimes the images are enlarged or upright or inverted, etc. And so we call this the magnification. The magnification here, H sub I is the image height, and H sub O is the object height. So it does make sense that the magnification would be the ratio of the image height to the object height, because that would tell you how big it is. But it's also related to the image distance and the object distance. And so there are some different values that you can get for M. First of all, if the absolute value of M, oh wait, I want to do this first. If M is greater than 0, then your image is upright. If M is less than 0, then it's inverted. Now, if the absolute value of M is greater than 1, then your object is enlarged. And if your absolute value of your magnification is less than 1, then your object is reduced. It's smaller than usual. And so those are the values of M we can have. So you can get any value for M, from basically anywhere. Any positive value, any negative value. If it's a fractional value, it's a reduced image. If it's a greater than 1 value, it's enlarged, etc. Positive and negative tells you whether it's upright or inverted. And also, obviously, this value can be positive or negative, the image height. If it's upside down, it should be negative. If it's right side up, it should be positive. And so that's some of the basic information that we need to deal with mirrors, both plane and spherical. And so after this, we'll look at lenses.